Hi, kids. So, I'm going to give you a little introduction to rotational motion and torque right about now. So, if you remember, one of the very first things, in fact, the very first question that I asked you at the start of physics was this: in order for something to stay moving, what has to be applied to it? And if you want to pause and think about it, you can. But most of you answered it wrong. Most of you at the time said force because even though you memorized an object in motion stays in motion, you didn't actually understand it. And now, of course, you actually understand it. And so you would look at that and go, in order for something to stay moving, what has to be applied to it? You would say nothing, because you know what? An object in motion stays in motion along a straight line, because that's what Newton's first law says. And that is inertia. If an object has inertia, it wants to keep going in a straight line. And then you might ask, well, what does a force do? Well, a force causes an object's motion to change. So let's remember that. So, and really it was a net force causes motion to change. So whenever there's a net force acting on an object, its motion is going to change. Well, how could it change? It could speed up, it could slow down, it could change direction. Yes! Oh, if something speeds up, slow down, or changes direction, what is that? That is acceleration. Because, yes, of course, F net equals ma. So if there's a net force acting on something, it's going to accelerate. The rate of the acceleration depends on the net force. It depends on the inertia, how much mass. Remember, force is a vector, so, it points in a certain direction. So there we have it. Lovely. Okay. So if we talk about rotation, guess what? We're going to start the same way. In order for something to stay rotating, what has to be applied to it? Well, if you want, you can pause and think about it. But guess what? Oh, yeah. The answer is nothing. Because guess what? Just like we said over here, that due to inertia, an object in motion stays in motion along a straight line. Well, over here, it's the same thing. There's going to be something called rotational inertia. And if something is rotating, it's going to want to stay rotating in the same direction as rotating. Because, that's Newton's first law for rotation. An object that's rotating is going to stay rotating unless acted on by a net instead of a net force. It is going to be a net torque. So a net force causes motion to change. Well, guess what? Net torque. Net force causes, there should be an S, causes rotation to change. So over here, where we said, well, how do you change motion? You speed up, you slow down, you change direction. Well, over here, how do you change rotation? You rotate faster, you rotate slower, or you change the direction that you're rotating. Okay? Net torque, okay, the symbol for torque, it's a Greek symbol tau. Okay, it looks like that. Kind of a fancy T. You can find it on the equation sheet on there. But the formula for torque is going to be R perpendicular times F. So let's talk about what the heck does this actually mean. But just keep in mind, okay, where, again, net force causes acceleration, net torque is going to cause rotational acceleration or angular acceleration, which just means if there's a net torque, it's going to rotate faster, it's going to rotate slower, or it's going to change the direction it's rotating. Okay, should make sense. But let's talk about what this actually means here. So the net torque depends on the force, and it depends on this R. What is this R? Well, this R is something called the lever arm. What is the lever arm? So let's talk about this. This is the lever arm. Okay. The lever arm is the distance from this force to the axis of rotation. When we talk about something is rotating, it has to rotate around something. What is that called? It's called the axis of rotation. So if I have, for example, I think you can see this, if I have a door, for example, where the hinges are here and the doorknob is there, the axis of rotation for my door would be right there. And then this lever arm is the distance from the axis of rotation to where you're applying the force. Well, most of the time when you open a door, you use the doorknob, so you're applying the force right there so that your R would be that distance. Okay? Yeah, hopefully that makes sense. The reason there's a little perpendicular thing right here is if I want to push the door, I would push this way because that way is perpendicular. I wouldn't stand this way and try to pull like this. That doesn't make sense. I would push that way because it's going to be perpendicular, okay? But that's how a door works. But a lot of times we're going to be talking about things like, hey, let's say I have this meter stick or a stick. And I don't know, let's say it's rotating around the center. So I'm going to put an X right there where the axis of rotation is. So it would be like, hey, I have this meter stick and I'm holding it right in the middle and it's going to rotate like this. See, it's rotating around there. That's the axis of rotation. Well, if I am applying a force here, let's say I'm applying a force there, I'll call that force 1. And then, I don't know, over here, I am going to apply a force this way, and I'm going to call this force 2. Okay, well, actually, I'm going to make force 2 a different color, just so we can see that they're different, and we can see things. So my force 2 would be this way. Well, if I wanted to figure out the torque for each of those, you're going to take your pencil. So take a pencil, because you're taking notes. And then you're going to hold your pencil right in the middle. Hold your pencil right in the middle. Why am I doing that? Because that's going to be my axis. And then you would say, hey, force is a vector. It has direction. Torque is a vector. It also has direction. But for the purpose of our class, the direction is going to be, this force is going to cause it to go clockwise. Hey, look, that force causes it to go clockwise. Does everybody see that? Hey, look, this force also causes it to go clockwise. Oh, obviously all forces cause things. No, they don't. So you have to figure it out. So how do you figure it out? You draw this, you put your pencil down, and you figure out which way it causes it to rotate. In this case, both of these would cause it to rotate clockwise, so they would both have clockwise torques. But if I was drawing in, there would be the lever arm for the first force from here to here. Do we see how it's perpendicular? We'll talk later if it's not perpendicular. And then this would be the lever arm for 2. You can see that, again, it's perpendicular, okay? If I have something like a teeter-totter, so let's just do one of these examples. But in this example, does everybody see this torque and this torque both cause it to rotate clockwise, okay? Where if I have an example like this, so let's say I have a teeter-totter that's rotating here, and I don't know, there's somebody standing on it here, and there's somebody else, there's a kid standing on it. Maybe there's kids standing on it here, and there's a big dude standing on it over here. And if you wanted to find the torque from each person, it would be, all right, well, this force, there's going to be a force from person 1 going down. There would be a force from person 2 going down this way, And then the lever arm for 2 would be there to there. The lever arm for 1 would be there to there. And then if you were to do this, you would say, hey, look, I'm going to hold this right here, and then I'm going to figure this out. F2, hey, look, that's going to cause it to go clockwise. F1 is going to cause it to go counterclockwise. So again, it's not the direction of the force, it's the direction of the rotation, and then you could work things out. Hopefully that makes sense. Okay? And bye, kids. Bye, kids.